Hey everybody, welcome to today's lesson on pulse sequences in MRI. This lesson focuses on conventional spin echo pulse sequences. We will discuss how conventional spin echo sequences work and discuss their advantages and disadvantages. Conventional spin echo pulse sequences are a fundamental concept and process in MRI, so understanding how they work is important. Let's begin. Conventional spin echo, or CSE, is a pulse sequence used in MRI to generate high-quality images by rephasing spin dephasing caused by inhomogeneities, variations in the magnetic field, and spin-spin interactions. Initially, a 90-degree radiofrequency, or RF, pulse tips the net magnetization vector, or NMV, from its alignment with the main magnetic field, B sub 0, into the transverse plane, B sub 1. This action also causes the spins to precess in phase around the B sub 0 axis. Due to magnetic field inhomogeneities, the precessing spins begin to dephase, leading to signal loss. The introduction of a 180-degree RF pulse reverses the phase dispersion of the spins, causing them to rephase and produce a detectable signal known as the spin echo at a specific time after the initial pulse. This rephasing creates the conventional spin echo. Although any number of spin echoes can be created in a sequence, conventional spin echo sequences generate one. Let's go more in depth on this concept. Spin echo sequences using one echo are used to produce T1 weighted images, proton density weighted or PDW images, and T2 weighted images. After the initial 90-degree RF excitation pulse, a single 180-degree RF rephasing pulse is applied that generates a single spin echo. Remember, TR is the time between RF excitation pulses, and TE is the time from the start of the RF excitation pulse and the peak of the signal from the spin echo. Since the NMV of fat and water recover at different rates, a short TR emphasizes the differences between the tissue's T1 recovery times, while a short TE means that little T2 decay occurs, so the differences between the tissue's T2 decay times are minimized. Let's discuss the advantages and disadvantages of conventional spin echo pulse sequences. Advantages: predictable image quality. Because of the well-characterized, well-understood relationships between extrinsic and intrinsic contrast parameters, spin echo sequences allow for a high degree of control over the image acquisition process. High image quality. CSE provides images with excellent tissue contrast, making it invaluable for diagnosing a wide range of conditions. Reduced susceptibility artifacts. The conventional spin echo technique is less susceptible to magnetic field inhomogeneities compared to gradient echo sequences because of the RF rephasing pulse, resulting in clearer images. Versatility. It can be used to image various body parts and conditions, offering flexibility in clinical settings. Disadvantages: longer scan times. The process of acquiring multiple echoes for image formation results in longer scan times compared to other sequences, which can be uncomfortable for patients. Sensitivity to motion. Patient or physiological motion during the scan can affect the quality of the images. Let's take a look at a practice question. In a conventional spin echo MRI sequence, how does altering the echo time, or TE, and repetition time, or TR, affect the contrast of the resulting image? A. Increasing both TE and TR maximizes T1 weighting, making it ideal for visualizing anatomical details. B. A short TE and a long TR enhance T2 weighting, allowing for better visualization of fluid-filled structures. C. A short TR and a long TE predominantly enhance T1 weighting, making it useful for detecting fatty tissues. D. A short TR maximizes T1 weighting, and a short TE minimizes T2, while a long TR minimizes T1 weighting, and a long TE maximizes T2 weighting. Correct answer: D. A short TR maximizes T1 weighting, and a short TE minimizes T2. In summary, conventional spin echo, or CSE, is a pulse sequence used in MRI to generate high-quality images by rephasing spin dephasing caused by inhomogeneities in the magnetic field.